This is quite simple. We have the position vectors of A and B, and we have to find in question number A the modulus of the vector AB. So the vector AB equals to OB minus OA by the direction vector rule. So OB is 4i plus 3j minus 2k in the column vector format, and OA is I minus j plus 3k. So it turns out to be 4 minus 1 is 3. Then we have 3 minus minus 1 is 4. Minus 2 minus 3 is minus 5. So modulus of AB would be square root of 3 squared plus 4 squared plus minus 5 squared, and this is going to be 9 plus 16 is 25. 25 plus 25 is 50, square root of 50. In question number B, we have to find the equation of L1. Remember, when you have L1 that passes through 2 points A and B, then the vector equation of the line, this is basically the universal position vector format, is going to be OA plus any arbitrary constant lambda into the direction vector AB, because we don't know how long this line going to be, so we write lambda into AB. So we find an arbitrary point somewhere around here, suppose. So that is going to be AB. Lambda into AB is going to be, that's how long that line is going to be. So first of all, we can write this directly. R equals to, so OA plus lambda AB. So OA is I minus j plus 3k plus lambda. AB is going to be 3, 4, minus 1. Now it is important to note AB is going to be the direction vector. So if there is any number that can be taken common and put into the scalar, we have to take that common. Here we can take nothing common, so we'll just write 3i plus 4j minus 5k, and that's it. In question number B, another equation is given. This is L2, and we have to show that the point B lies on that. Remember, if a point lies on a vector line, it means for that particular point, the value of the scalar lambda or mu has to be same for each coordinate. To show that a point lies on a line, we have to show that each value of the lambda or mu are equal. So first of all, let's write down the universal position vector format for L2, this one. So 6 plus 2 mu I, 4 plus mu j, and minus 3 minus mu k. So that's the universal position vector. That means this is OB. So this is equals to OB, same as this, because it's the universal position vector. So OB is equals to 4i plus 3j minus 2k. Since this and this, they're equal, let's see whether the three values of mu are equal or not. So for I equals to I, 6 plus 2 mu equals to 4. Therefore, mu equals to 4 minus 6 is minus 2, divided by 2 is minus 1. And j equals to j is 4 plus mu equals to 3. Therefore, mu equals to 3 minus 4 is minus 1. And k equals to k, we have minus 3 minus mu equals to minus 2. Therefore, mu equals to minus 1. So since mu equals to mu equals to mu, the point B lies on L2. That's it. Question number D is find the angle between L1 and L2. For this, we need the direction vector of L1 and direction vector of L2. So which is this one? So this over here is the direction vector of L1, and this over here is the direction vector of L2. So we can easily find the angle. So cos theta equals to direction vector of L1 is 3i plus 4j minus 5k dot direction vector of L2 is 2i plus j minus k divided by modulus of direction vector of L1 is 3 squared plus 4 squared plus minus 5 whole squared, square root of 2 squared plus 1 squared plus minus 1 whole squared, and this turns out to be 3 into 2, I into I is 6, plus 4 into 1, j into j is 4, plus minus 5 into minus 1 is 5, and this is going to be square root of 9 plus 16 is 25, 25 plus 25 is 50, square root of 4, 2 square is 4, 4 plus 1 is 5, 5 plus 1 is 6, so this is going to be 6 plus 4, 10, 10 plus 5, 15, square root of, this is 6 6 5s are 30, 300. And do we have to find theta or do we have to find just cos ratio? Find the size of the acute angle. So we have to find theta. So therefore, theta equals to cos inverse of 15 by square root of 300. And this turns out to be cos inverse 15 divided by square root of 300. 30 degree. That's pretty cool. In question number E, we have to find the shortest distance from A to L2. They said hence or otherwise. This usually means if you don't do hence, otherwise you're going to be in serious trouble. So let's follow hence. The story so far goes like this. First we found there is a line L1 and it passes through the point AB. So this is L1. Second, we proved that the point B over here also lies on L2. Then we found the angle between L1 and L2, which is 30 degree. And finally, we have to find the shortest distance, meaning the perpendicular distance from A to L2. So let me call the perpendicular distance H for height. And at first, in question number A, we found the length of AB, meaning the modulus of the vector AB. So this is square root of 50. So using a little bit of trigonometry in this triangle, we can write sine 30 degree equals to opposite by hypotenuse. So the opposite is height h and hypotenuse is square root 50. Therefore, the height is going to be square root 50 sine 30. We know sine 30 is half. So the height would be square root of 50 divided by 2. It's better to find this in decimal places. So this is going to be square root of 50 equals to divided by 2. So 3.54. A little note about calculation. Many people do this calculation like this. Square root of 50 divided by 2. In many calculators, this could turn out to be square root of 20. I don't know what it would happen here. This calculator understands it is square root of 50 divided by 20. But many calculator considers this to be square root of 50 by 2. That means 25 square root of 25. And it turns out to be 5. So be very, very careful how you calculate this. So we have a vector L, L1. And we have a point A which lies on that vector. We have to find a constant. Let's do this in the quickest possible way. So if this point lies on this vector line, meaning the universal position vector, then they would be equal for point of intersection rule. So let me write this down in the column vector format. So L1 would be 6i plus lambda I is 6 plus lambda I, 19j plus 4 lambda j, 19 plus 4 lambda j, minus k minus 2 lambda k, minus 1 minus 2 lambda. This is the column vector format of L1. And A, so OA would be 0, A, B. So since they are equal, we can write for 6 plus lambda equals to 0, lambda equals to minus 6. We know when a point lies on a particular line, the value of lambda for each coordinate should be equal. So for this, and next one, 19 plus 4 lambda, lambda is minus 6 equals to A. Therefore, A equals to 19 minus 24, it turns out to be minus 5. And minus 1 minus 2 lambda is minus 6 equals to B. Therefore, B equals to minus 12 minus 1, 11. So we got the answer. A equals to -5, B equals to 11. Question number B. The line L1 has a point P on it such that OP is perpendicular to L1. So it's the same question all over again. So we have this line L1. So we have the universal position vector of this. That means any unknown point on it is this. So this is point P and OP is perpendicular to L1. So the rule is the dot product is going to be 0. So dot product, direction vector of OP is OP itself, dot. Direction vector of L1 is the direction vector, which is given by this 1 plus 4j minus 2k. So the dot product would be 0. That is the rule for dot perpendicular lines. So let me use the column vector that is faster. So since we don't know what the value of lambda is for this point P, we can use the universal position vector, which is 6 plus lambda, 19 plus 4 lambda, minus 1 minus 2 lambda dot. The direction vector of L1 is I plus 4, so I 4 minus 2 equals to 0. That means the coefficient of I into coefficient of I, 6 plus lambda into 1 plus 19 plus 4 lambda into 4. So 19 into 4 is 4 9s are 36, 4 1s are 4, 76 plus 4 4s are 16 lambda. Minus 2 into minus 1 is plus 2. Minus 2 into minus 2 is plus 4 lambda equals to 0. We have lambda plus 16 lambda is 17 lambda plus 4 is 21 lambda. We have 76 plus 6 is 82. 82 plus 2 is 84, so plus 84 equals to 0. Therefore, lambda equals to minus 84 divided by 21, which turns out to be minus 4. Therefore, let's find the value of position vector of OP by putting it in the universal position vector. So this is going to be 6 plus lambda. That means 6 minus 4, which is 2. Then 19 plus 4 lambda, 19 minus 4 4s are 16. 19 minus 16 is 3. Minus 1 minus 2 lambda, lambda is minus 4. Minus 1 plus 8, that is going to be 7. So we have to find the position vector of P. So we can either write it in the column vector format or in IJK format. 2i plus 3j plus 7k. One final question is left. We have to show that A, P and B are collinear, meaning on the same straight line. That means we have to show that they have the same direction vector. That means in question number C, if we have a line like this, suppose we have A and we have P and we have B, we have to show that any two vector on this line has the same direction vector. So let me start with AP. So it is OP minus OA. So OP is, we just found it, 2, 3, 7 minus OA. A is 0AB. So 0A is minus 5, B is 11. We found this. So this is going to be 2 minus 0 is 2, 2 minus minus this is 8, 7 minus this is minus 4. If we can take, it's very important for direction vector, you have to take something common. We can take 2 common and whatever is left over is direction vector 1, 4, minus 2. So this is the direction vector for AP. AP is 2 into this direction vector. Now we have to find PB. So PB vector is OB minus OP. So OP we know is 2, 3, 7. What is OB? Do we know this? 5, 15, 1. 5, 15, 1. So 5 minus 2 is 3, 15 minus 3 is 12, 1 minus this is minus 6. So if we take 3 common, it would be 1, 4 minus 2. Now notice they have the same direction vector such that we can write since AP and PB vector have the same direction vector, they are collinear, meaning in the same line. That's the collinear rule. Now we have to find the ratio. So AP divided by PB equals to 2 into direction vector divided by 3 into direction vector, and this direction vector cancels off, so I'm not giving the vector sign because all I have to do is find the ratio. So what ratio do we have to find? AP is to PB, that's it. Therefore AP is to PB is 2 is to 3.